Okay, we're still waiting for two more. Homework questions. That'll kill 2 minutes. Or 2 seconds. Okay. Well, so I should be getting a whole bunch of submissions for Chapter 5 homework imminently. No. It's the end of the semester, nobody cares anymore. Yeah, okay. I'm right there with you. Well, only 3 more weeks of classes at least, and not even full weeks at that. Okay, this is the last week we're dealing with eigenvalues. So I posted a Canvas quiz on Chapter 6, eigenvalues. Of course, nobody got notified about it again, so that's precious. Okay, all right, now we have everybody. I apologize in advance for the number of questions on the quiz. So I took the concept check from each section in Chapter 6, and that was like a zillion questions, and I cut out a whole bunch, and even more than I wanted to, because some of them were about essential properties and such. So by the time I whittled as much as I could, there were still 16 of them. But as you're suffering through answering them, just remind yourself that I'm the one who gets to suffer through grading them. So.
When is that quiz due?
Does that matter? Okay. Well, okay. The due date I put in Canvas is a week from tomorrow. Yeah.
And it's not going to lock us out or anything. Because, like, I know in other classes when something's past due, it, like, locks it.
Oh, yeah. But,
Okay.
yeah. Okay. And then I also posted homework for Chapter 6. So you have 2 options. So one is similar to the other homeworks that we've had, just problems from a book. Not much going on the coding front. That's option number 1. Option number 2 is if you really would prefer to code instead of prove something or a bunch of things, then you can do that instead. So there's a project I've been given for several years where really there's one task, and that is write a MATLAB program consisting of a certain number of functions whose job it is to find the eigenvalues and eigenvectors of a symmetric matrix. So it's going to use the QR algorithm that I've been covering, although it'll be this stripped down symmetric version, which I'm going to cover today. So the handout is posted. So like these are functions you have to write. The first 2 actually I'm giving to you, one for givens rotations and one for householder. And then you fill in the rest of the pieces. There's some pseudocode given in Gollop and Van Loan, because it's not actually it might be in my book. I just didn't think about it this time around. But I've reproduced those pages from Gollop and Van Loan. So if you want to try a nice little coding challenge, you could say you wrote an eigenvalue finder, then you can do that. So you could pick one or the other. Now, I am not opposed to offering some bonus to those who do the coding one. Because my hunch is people might be less likely to choose that, but it'd be nice if somebody did. So I'm willing to do that. So either way, whichever assignment you choose, for it will be due basically as late as anything can be due. The last day of finals, which is Thursday, May 9th. Because then grades have to be in on the 13th. Okay, yes?
Besides the symmetric algorithm, handout, PDF, and algorithms,
Yeah.
PDF, what does that
of it. So you're on the site.
Yeah.
Yeah. So the handout is just the assignment description. Yeah. You can look at the documents before you ask me about them. The algorithms are there's 2 pages I've photocopied from Golub and Van Loan that describe certain pieces in pseudocode, so that you would implement those in MATLAB. Okay, and then you can also see on the assignments page the first 2 functions, which actually these functions were assigned as homework, but I didn't trust you all as implementations because practically none of you got full credit for it. So I posted my own. Okay, so for givens and householder. Okay, so let's see. Yes. Just out of curiosity, how many of you might be inclined to choose the coding one? Okay. 2.
I'm gonna look at it.
Okay. Okay. All right. Is response affected by my offering bonus? Okay. Okay. All right. Well, dang. Well, don't be wusses now. Although, one of our former students, after finishing her bachelor's here, went on to, I think it was South Alabama, for a master's program, and took a numerical linear algebra course, so much like this one. Studied all the same things about singularity decomposition, pure factorization, all that. And there was not a single coding problem in the whole course. It was all working on stuff on paper. It's like, kind of the point of this whole field is to code things up and have them do stuff. So, yeah. Which is why I'm hoping at least one of you will choose this. So, actually, I think what I used to do in this class, I actually used to require it, and then because the students at the time were such whiny butts, I introduced the other option that had some like theoretical problems in there. So, and to me, both are important. So, and I'm not feeling sadistic enough to require both. So, but if nobody takes it up, even with the dangling of a carrot of bonus, then I might have to think differently next time around. So, future students can thank you for their pain. Okay. All right. So for so all this time we're covering finding eigenvalues for just a general matrix. Really no assumptions added, but now we're going to assume symmetry. Now, I have too much in these notes to cover in one day, so I'm just going to pick out stuff I like. Now, at least that's what I'll spend the most time on. So, if A is symmetric, a lot of things work out nicely that we do not have in the unsymmetric case. First, we have the eigenvalues are real. Okay. And when I say symmetric, maybe A equals A transpose if it's a real matrix, or A equals A Hermitian transpose if it's complex. So in that case, I would not really say A is symmetric. I would say A is Hermitian. Now, if A equals A transpose and it's complex, we call it complex symmetric, which isn't really as nice. But in either one of these cases, we get real eigenvalues. From this point on, just for simplicity, I'm just going to assume we're talking about a real matrix that is symmetric. Okay. Another thing that works out nicely is that the Shor vectors equal the eigenvectors. So the Shor decomposition has this form, QdQ transpose, where D is diagonal. As I mentioned last time, for this unsymmetric case, once we find the eigenvalues, we get to real Shor decomposition. We still have a whole lot of work to do, which I only got into a little bit, to get the eigenvectors, but here there is no extra work. Once you have a Shor decomposition, you're done, you have everything. So the eigenvectors are actually orthogonal. Now, how do we compute eigenvalues in the symmetric case? We do use the same methods that I covered for the unsymmetric case. We have the power method. Now, the power method will work the same way, and the algorithm itself will be exactly the same. But one nice thing that happens, it converges quadratically to get the largest eigenvalue and the eigenvector that goes with it. Whereas in the unsymmetric case, we only have a linear convergence. Now, it still depends on how spread out the eigenvalues are. Like, you want the first eigenvalue, the largest one, to be much larger than the rest for faster convergence. That still applies here, but at least you get this boost to convergence. Now that's if you're after like a selected eigenvalue. If you want all of them, you still have the QR algorithm, but I've just been covering for the unsymmetric case lately. So instead of presenting a QR algorithm all over again, making changes for the symmetric case, I'm just going to give a rundown of what really is different about the QR algorithm in this case. All right. So if you want to consider doing the coding option for homework 4, these points are going to be relevant. So in the QR algorithm for the unsymmetric case, the very first thing we do is we use Householder reflections to reduce A to Hessenberg form. Well, we're still doing that, but if you have a matrix that is Hessenberg and symmetric, that is tridiagonal. because you have a matrix, I'll use my x's to make a matrix Hessenberg. So here is a 5 by 5 unsymmetric Hessenberg matrix where we have all these zeros down here. But by being symmetric, these entries that are 0 down here must lead to having 0 entries up here, too. So in a Hessenberg matrix, everything below the first subdiagonal is 0. Well, by symmetry, that means that everything above the first superdiagonal must also be 0. So only this part, the diagonal, one subdiagonal, one superdiagonal, those are the only parts of a matrix that can have non-zero entries. So that's why you get tridiagonal. So what happens is you're trying to reduce A to diagonal form this time, because before you want an upper triangular. But if a matrix is upper triangular and symmetric, same idea. It's got to be diagonal. So first thing you do makes it pretty close to diagonal already. You've wiped out almost everything. You just have these 3 diagonals left. So the process is exactly the same. Using Householder reflections, it's just get a much nicer result. Okay. Second difference is all the stuff I spent so much time on last week about the double shift, the implicit double shift, and Francis QR step, don't need any of it. Because the only reason we had that stuff in the first place was because of the possibility that A could have complex eigenvalues. So we don't have any complex eigenvalues. They're all real. So none of that's part of the picture. Now we could use the single shift strategy that I described last time, where you use the NN entry. That does work, but you can do better. Use the Wilkinson shift. Now what is the Wilkinson shift? Your shift, which I'll call mu, is equal to the eigenvalue of this lower right 2 by 2 block. So you look at the last 2 rows and columns. Of a matrix. You compute its 2 eigenvalues, which are real. And you pick the closer, which one of these eigenvalues, you get 2 of them. You pick the one that's closer to TNN. On the non-coding homework, there's a problem to derive this. So it's an exercise involving quadratic formula. That's what you use to compute the eigenvalues of this in the first place. All right. Now, I mentioned last time, if we use the NN entry, so TNN as the shift, that worked quite well because we get quadratic convergence. But the Wilkinson shift converges cubically. So you can save yourself some iterations of a QR algorithm by using this shift. There's a Wilkinson wrote book, this is called The Algebraic Eigenvalue Problem, that pretty much has everything one would need to know about computing eigenvalues. So there's probably a lot of secrets in there that we could use today, but they're buried in a book somewhere nobody knows about them. Other differences. Not so much in what you do, but just what ends up happening is a QR step where you do, if you tridiagonal matrix, you shift it, take the QR factorization, and then you update T by multiplying the factors in reverse order, and then putting a shift back. So we still do all of that. This takes only order n floating point operations, whereas in the unsymmetric case, it took order n squared. So it's a whole lot cheaper when it's symmetric. And the reason why is each Gibbons rotation that you use to reduce this matrix to upper triangular form and then to multiply the factors in reverse order, that's all done using Gibbons rotations, whether it's symmetric or not. But in a symmetric case, you're rotating rows or columns that only have like 3 or 4 non-zero entries. In other words, a number of non-zero entries that does not depend on n because of the symmetry. You have all these entries being 0 up here. So the same process in the unsymmetric case just happens to require a whole lot less work. Now, for the unsymmetric case, I mentioned that what we're trying to converge to is a matrix that's not necessarily upper triangular, but it's quasi-upper triangular. You may have like 1 by 1 or 2 by 2 blocks on the diagonal. So it's kind of a pain to check for that. But in the symmetric case, everything is real. You're not going to have 2 by 2 diagonal blocks. So you just need to look at the subdiagonal entries for decoupling. So for example, if you have your tridiagonal matrix, so it's symmetric and Hessenberg. And let's suppose you perform this sequence of steps a number of times, and let's say this entry turns out to be 0, then I've drawn this picture before. Then it tells you that there's decoupling, so then your next QR step would be either on this matrix or this one. Doesn't really matter which. You're going to get to all of them eventually. So you're just looking for a unreduced Hessenberg block. But so the monitoring of subdiagonal entries is easier to do in a symmetric case because you know you eventually want to make all of these entries 0. So what you can do, for instance, is you can start from the bottom and look for first non-zero on the subdiagonal. You say, oh, that's where your block begins. So let's suppose, for instance, that these were 0 also. So you keep looking, and you see, oh, here's a non-zero entry. I know that this is the end of my unreduced block. Then I keep checking as long as it's non-zero here. Then you keep going until you find the number 0 here, or until you reach the end. And then you know, oh, I have an unreduced tridiagonal block. Then I can perform these QR steps just on that block to keep reducing to diagonal form. So this monitoring for convergence is a bit easier in the symmetric case than the unsymmetric. I will say that this part, for those who choose the coding option, is probably the one that's it's probably the hardest part, just because you have to make sure you have your indices right. Everything else in that assignment, you are basically taking algorithms that are provided to you, either in my book or in Galvin Van Loan, that are given to you in pseudocode, and you're just coding those up in MATLAB, which you've had some practice doing already from the other homeworks. The part that's a little tougher to figure out is how you handle finding the right block. You basically have to keep track of which indices, like what's the starting and ending index of your unreduced block, and how does that change from one iteration to the next as one of these entries becomes 0. But other than that, you find an unreduced block, then you just call these other functions to work on it, and you go from there. Okay, so for the symmetric case, it turns out that the work involved. So this part is still order n cubed, unfortunately, because you have a matrix that's full initially, and then you're wiping out all these entries above and below these free diagonals. But after the Hessenberg reduction part, it only takes order n squared operations to do the rest for an n by n matrix, which is quite unusual. But it's because you've wiped almost everything out already. So everything. So this is. So if you have a matrix that is sparse and symmetric at the beginning, then you can find its eigenvalues and eigenvectors very quickly compared to a general matrix. And it's order n squared is still kind of a lot, but it's a lot nicer than for other problems. And tridiagonal symmetric matrices are of considerable importance. For example, for differential equations, solving PDEs or ODEs, like boundary value problems or initial boundary value problems by finite differences. The matrix for that is a tridiagonal symmetric matrix in many cases. So getting some of its eigenvalues and eigenvectors is not out of the realm of possibility. Okay. So that's the idea of what's different for the QR algorithm for the symmetric case. Make sure I haven't left out anything. Okay. So the implicit Q theorem applies, and it is used, but it doesn't really play the same essential role as it does for the unsymmetric case. Okay. Okay. Now, so I want to talk about some approaches for computing eigenvalues and eigenvectors for a symmetric matrix that really are only effective for a symmetric matrix, and very different than the methods I've covered here, beginning with the unsymmetric case. Actually, these relate to problems that I considered assigning for homework, and in the end decided not to. So I guess I'm working them out here. You can thank me later. Yeah.
Even though you already taught this value process in assignment,
Sorry, what?
Yeah, about the blocks.
Yeah.
Why you saying if there is one entry that is 0 in the sub-diagonal, then you have to reduce the other ones within the sub-blocks to 0 as well.
Yeah, because the thing is, ultimately you want to reduce this entire matrix to diagonal.
Okay.
But the thing is, initially you're performing this QR step on the whole matrix. But once a single entry like this one turns out to be 0, you don't have to keep applying this to the whole matrix. you can do it on these smaller blocks. So just for efficiency's sake. So what happens is once this becomes, say this becomes 0 first, then I could be working on this block until like maybe that goes to 0, and then maybe a few iterations, and then it decouples again, and so forth. So at some point, you're carrying this out on the probably, I guess, the largest unreduced block that you can find until you don't have any more. And if you carry this out yourself in MATLAB on a random symmetric matrix, that's what you'd see, is that like one by one, these subdiagonal entries would end up going to 0. Although, if you have eigenvalues that are clustered close together, then that convergence is slower. So a very different approach that's really not appropriate for computing all the eigenvalues, but maybe selected eigenvalue-eigenvector pair. It's called Rayleigh quotient iteration. So not Raleigh like North Carolina. There's an extra Y in there. Now, what is a Rayleigh quotient? All right, so this is a very useful expression on its own, regardless of Rayleigh quotient iteration. My page is in order. Okay. So it's a function of a vector x and a matrix A. So it's just x transpose AX over x transpose x. And no, you cannot cancel the x's and get A. What you do get, though, so if AX is equal to lambda x, so if x is an eigenvector of A, then the Rayleigh quotient, you can work that out. It turns out to just be lambda. So given an eigenvector, the Rayleigh quotient gives you the corresponding eigenvalue. Now, Rayleigh quotient iteration is built from two things. One is a Rayleigh quotient, and the other is something I mentioned previously, inverse iteration. So for inverse iteration, which is the power method, a variation on the power method, you choose a vector x naught, a unit vector, and you also choose a shift mu. So in a loop, until convergence, you solve this system with A minus mu times identity. The idea is if mu is not an eigenvalue of A, then this matrix is invertible, so you can solve that system. And then, like in the power method, you get your next vector in your sequence by normalizing and the idea is this is the power method applied to A minus mu I inverse. Because what you're doing here is to get zk, you're basically multiplying xk by a minus mu I inverse repeatedly. So, so the power method applied to that matrix. And what it does is it finds the eigenvalue closest to mu. Now, power method, the normal power method, which is multiplying by a, that finds the largest eigenvalue of a. Well, the largest eigenvalue of a minus mu I inverse is 1 over the smallest eigenvalue of a minus mu identity. So you're taking, so that's why it's the eigenvalue closest to mu. So like if I set mu equals 0, inverse iteration would just give me the smallest eigenvalue of a in magnitude. Now for inverse iteration, I've chosen my shift mu up front, and I just keep using that with each iteration. But what if we let mu vary from iteration to iteration? What if the information we get, because the idea is xk gets closer and closer to an eigenvector. Well, if xk is getting closer and closer to an eigenvector, the Rayleigh quotient is getting closer and closer to an eigenvalue. And if the shift that we use, mu, is getting closer to an eigenvalue, then this will drive my x's to an eigenvector more and more rapidly. So we're basically trying to create a positive feedback loop here. That solving this system gives us a better eigenvector, which by way of a Rayleigh quotient leads to a better eigenvalue, which is a better shift to get closer to an eigenvector and so forth. So by combining these two things, Rayleigh quotient and inverse iteration, that's how we get Rayleigh quotient iteration. Or RQI. I don't feel like writing Rayleigh quotient iteration out again. All right, so what is the algorithm for Rayleigh quotient iteration? It's very similar to that of inverse iteration. We just have to work the Rayleigh quotient into it. So we choose some initial vector, x naught, make it a unit vector. So now instead of choosing the shift mu arbitrarily, we're going to get it from the Rayleigh quotient. We keep updating it in our loop. So shift is going to be a Rayleigh quotient of xk with a. That's going to be xk transpose axk. If you compare that to a formula for Rayleigh quotient over there, you'll see there's a difference, but it is not a mistake. Can you tell me why? What did I leave out? Yes. How come it's okay to leave out the denominator in this case? What is 1? The magnitude. Yeah, because this x transpose x is the 2 norm of x squared. So, but I'm already making xk unit vector, so the denominator will be 1. Okay. Now I proceed with inverse iteration. A minus UK identity. The same system, I'm just using this shift that I've gotten using Rayleigh quotients. Then I go ahead and normalize ZK. So I can keep going. That's it. That's the algorithm. Now, this is going to find an eigenvalue, eigenvector pair. So xk will converge to an eigenvector, uk will converge to the corresponding eigenvalue. Now, we don't really know, can't really say in general which eigenvector pair is going to find. Which one depends on the choice of x naught. So, like, let's suppose that x naught is already close to the eigenvector for the largest eigenvalue, let's say. Then that's most likely the one it's going to find. That reminds me, I didn't assign this problem. Maybe I should have, but it's kind of a cool one to come up with. So it's one of the problems that's at the end of chapter 6. So because I have these explorations interspersed throughout the chapter, and I have these set of exercises at the end. So it's one of those where I provide a matrix that I made up and an initial vector, like the x naught. And the problem says, okay, you apply the power method to this matrix with this vector and explain what happens. And what does the power method do? What is the result of a power method? What? Yeah, it finds the eigenvector corresponding to the largest eigenvalue. But what I did was I chose an initial vector that was actually orthogonal to that eigenvector. The idea is if you take that eigenvector and put it out of the picture, okay, so if I take any old vector and make sure it's orthogonal to the largest eigenvector and use the power method, what should the power method find in that case? So any old vector. But I've removed the component of the first eigenvector out. So moved it out. That's redundant. But so in other words, the idea is I wanted to prevent it from finding the largest eigenvalue. So what should it find instead? No. Next largest. Yeah. So unless it happens to be orthogonal to that too, yeah, it should find the second largest eigenvalue in its eigenvector. I thought, well, okay, I'll try this out. I'll try the power method on this and study the convergence, see what happens. So I'm applying a power method, like several iterations, like 40-something iterations. And that's actually what I saw, that it's converging to the eigenvector for the second largest eigenvalue, as you'd expect. But then something really freaky happened, where all of a sudden the vector started to go in a different direction, because it was like really getting close to converging, and all of a sudden it started to turn. And then the eigenvalue started changing as well. I'm computing a Rayleigh quotient. I'm not using it as a shift. I'm computing a Rayleigh quotient just to see what it's converging to. And it started to veer off away from the second eigenvalue towards the first eigenvalue. It ended up converging to the first eigenvalue anyway. So I gave an initial vector, x naught, that was designed to have nothing to do with that first eigenvector. But it converged to it anyway. It took a while. Like, you had to run at least like 70-something iterations to see this happen. Can anyone think of why that might happen? Why would it go awry like that? Like how it appears to be converging to one thing, and at some point just veers off towards another. What could cause something like that? basically numerical analysis, how do you explain any strange phenomenon? Round-off error. It was all round-off. So round-off error, because, like I said, my initial vector was orthogonal to the first eigenvector. I explicitly removed that part of it. But as the computation proceeds, the round-off error causes there to be some small component of my xk in the direction of that first eigenvector. So it was orthogonal at the beginning, but it didn't stay orthogonal. There was just enough from round-off error to be not orthogonal to it anymore, and that eventually it started to take over. Yes, pretty much anything that goes really off of walls like that, it's probably because of round-off error. So, and I'm actually not surprised that it happened, because that's actually the point of the problem. But it was cool to actually see it happen like you'd expect, not just mathematically, but also in terms of floating point arithmetic, that would throw things off. Okay, now, so here we have the algorithm for Rayleigh quotient iteration that's going to converge to some eigenvalue eigenvector pair. And what I want to do now is explain why does this converge cubically? Okay. Now to show you why it does, I'm going to make the problem a whole lot simpler. If I write A in terms of its Schur decomposition, where D is diagonal, Q is orthogonal. And I'm also going to let xk equal to q yk. So that means that the Rayleigh quotient that I'm computing in the algorithm I'm going to replace A with its Schur decomposition. Oh. Okay, I need to transpose. Wait. Oh, actually, you have to figure work without transpose. Okay. Now, if I have xk is qyk, I can multiply both sides by q transpose. And I get yk is q transpose xk. Because q transpose q is identity. So now I can put that in here, and I get yk transpose d yk. So I've exchanged one Rayleigh quotient for another. So Rayleigh quotient with d and this vector. So that means that for purpose of convergence analysis, I can actually assume that D, that my matrix I'm working with is diagonal. I'm just going to work with D. So that simplifies things a whole lot. Because now I'm working in this space instead of this one. Okay. So I assume that D is this diagonal matrix with all the eigenvalues in the diagonal. And then I'm going to assume that my vector xk is going to be equal to E1, so the first column of identity, which would be an eigenvector of this diagonal matrix, except there's some error here. So epsilon pk. So in other words, it's a perturbation of an eigenvector. Because dE1 is equal to lambda 1 E1. E1. That's the eigenvector eigenvalue relationship. And I'm going to assume that pk is a unit vector. So what I have here, my xk is an order epsilon perturbation of an eigenvector. So it is, if I carry out one step of this algorithm and get xk plus 1, that should be a perturbation of an eigenvector too, but of what order? Order epsilon squared, epsilon cubed, what? So that's what we need to find out. Now, if I take the inner product of xk's itself, it has to be 1 because it's a unit vector. So then, if I actually work out what that is, so I have E1 plus epsilon pk, transpose that again. So now if I work that out, basically FOIL it. So E1 transpose E1 plus 2 epsilon E1 transpose pk plus epsilon squared pk transpose pk. Now E1 is a column of identity. It's a vector of 1 and then all zeros after that. So the inner product of itself is going to be 1. And then E1 transpose pk is going to be a first element of pk because of the way the dot product works out. Because E1 transpose anything takes the first row of whatever it is. And then pk is a unit vector, so this dot product is 1. So we just get epsilon squared. Now, this expression, this whole thing, is supposed to be equal to 1. But it has 1 in it. So that part has to be 0. Now, the only way that that could be 0, well, I can solve for P1k. So that's actually equal to, so I have to divide by minus epsilon over 2. So the point here is it's order epsilon. That's going to be here. But at least I can use that from this point on. That is equal, have as equal minus epsilon over 2. Okay. So, but these other entries of pk, they could be literally anything as long as the overall vector is a unit vector. But within that constraint, any other numbers are possible. Okay. So now I'm going to step through this algorithm. I need to figure out my shift. I need to solve this system, which will be easy because it's a diagonal matrix, and go from there. So my Rayleigh quotient R of xk and D, my diagonal matrix, that's going to be 1 plus epsilon pk transpose D, oh sorry, not 1, but E1. E1 plus epsilon pk. All right. So if I, now the thing is, if I FOIL this out, you get E1 transpose DE1. So it's going to work out much like before. I have 2 epsilon PK transpose DE1. I can combine those terms because D is symmetric. And then I have epsilon squared PK transpose D PK. All right. So I want to try to simplify this as much as I can. Now, D is this diagonal matrix over here. So E1 transpose anything E1, that's the 1, 1 entry. So that's going to be lambda 1 for the first term. And then I have 2 epsilon. So DE1 is lambda 1 E1. So what I have is lambda 1, and then I have E1 transpose PK, which is P1K. But I know what that is. That's minus epsilon over 2. And then I have this expression, PK transpose DPK. Unfortunately, I can't really simplify that many. So best I can do, what? Yeah. Yeah. Okay. So lambda 1 is, sorry, my Rayleigh quotient is pretty dang close to an eigenvalue because these terms with an epsilon squared in them are quite small. Okay. Now, I need to leave this algorithm up here because I'm still using it. So now I have to carry out this step, solving a system, equations. Thankfully, the matrix involved is diagonal, so it's really easy to do. So ZK is equal to A minus mu, it's not A, D. D minus mu K identity inverse XK. Now, this inverse matrix that we have here, so we have 1 over lambda 1 minus mu K, 1 over lambda 2 minus mu K, and so on, all times xk. So all I have to do is take the individual entries of xk and multiply them by the corresponding diagonal entries that we see here. So the idea is I'm going to look at the first entry of zk and then an arbitrary other entry so we can compare. Now, so z1k, first entry, so that's going to be x1k over lambda 1 minus mu k. Now mu k is my shift that I have here. So now I get to substitute that in here. So x1k is the first entry of xk. So that's going to be 1 plus epsilon p1k over lambda 1 minus lambda 1 minus lambda 1 epsilon squared plus epsilon squared pk transpose d pk. And this works out pretty nicely. Because up top I get 1 minus epsilon squared over 2. And then down below, the lambda 1s cancel out. So I get lambda 1 epsilon squared minus, actually the whole denominator is order epsilon squared. Okay, is there any questions about up to this point? Okay. So because epsilon is small, epsilon squared is going to be extra small, but it's a denominator, so it's going to make this entry rather large. But that's why we normalize zk from one iteration to the next. But now you're going to look at what about the other entries of zk? So zik, so that's going to be the corresponding entry of xk, which is going to be just epsilon pik, which we don't really know anything about. We just know that this pik is less than 1 in magnitude, just because the whole vector of k is a unit vector. And then down below, I have lambda I minus mu k. So I have lambda I minus lambda 1 plus lambda 1 epsilon squared minus epsilon squared pk transpose dpk. I've already distributed the minus in there. So here we do not have the cancellation that we did before. So let's just cut to the chase. What is the magnitude of each of these entries in terms of epsilon? The first entry is order epsilon to the minus 2, whereas this is order epsilon. Because we have the epsilon here in the numerator. The denominator, because of the lambda I minus lambda 1, is order epsilon to the 0, because there's no cancellation happening down there. So, if we look at the gap between orders of magnitude, it's 3. In other words, so zik, I greater than 1, is order epsilon cubed times z1k. So in other words, once I normalize it to get my new vector, xk plus 1, so this is equal to E1, if I were to work it out entirely, E1 plus something that's order epsilon cubed. So once I went through all the trouble of normalizing it, which I don't really need to do. The point is we can see this gap in the order of magnitude between entries that's order epsilon cubed. In other words, like this entry divided by this one. If you just carry out the division, you get something that's order epsilon cubed. So that's why we can say there's cubic convergence. That if xk is an order epsilon perturbation of an eigenvector, xk plus 1 is an order epsilon cubed perturbation of an eigenvector. It means, in other words, it's much, much closer to an eigenvector than the previous one, resulting in extraordinarily rapid convergence, because you don't normally see cubically convergent algorithms. So probably will only have to carry out like very few iterations, like maybe 2 or 3, depending on how good your initial guess is, and then that's it. You're done. So, unfortunately, we have the expense of solving this system. Can't get around that. But if you only have to, like, what if it's a sparse matrix, like tridiagonal or something, and so then solving systems is cheap. Or maybe you can use the iterative method. Then this works quite well. Now, not something you'd want to use to find all the eigenvectors, but for finding selected eigenvectors, it's a good idea. Okay. So any questions about all this gobbledygook that happened here? I know, 6 o'clock, everybody's brain is fried. Okay. Okay. Now, let's see, I only have 15 minutes. Okay, did all that. Okay. The last thing to cover, again, something else I considered. Yeah, so actually, I thought about assigning this as a homework problem, but so. You're welcome. So something else I considered assigning as a homework problem, decided against, is also related to approximate eigenvectors, or at least invariant subspaces. This is something. So another problem I had considered for homework problem and rejected was all of this here. Rarely quotient iteration is only for a symmetric matrix. Inverse iteration with a fixed shift you can use for any matrix, symmetric or not. But this analysis here would not work for an unsymmetric matrix, because I'm relying on the fact that your sure decomposition, like A equals QD Q transpose, that you have that sure decomposition where a matrix in the middle is diagonal, whereas the same for sure decomposition for unsymmetric matrix, the matrix is upper triangular. So all the stuff I did here just would not apply. Okay. So, all right. So let's suppose I have matrix Q1 that is n by R orthonormal columns. So Q1 transpose Q1 is an R by R identity matrix. All right. Now, so if the columns of Q1 span an invariant subspace, then we have this A Q1 is equal to Q1S. And S is equal to Q1 transpose AQ1. Also, from what we've seen before, the eigenvalues of S are contained in the eigenvalues of A. So you can use S to at least get R selected eigenvalues of A. And also, it leads you to the corresponding eigenvectors. But what I want to talk about is the case where the columns of Q1 do not span an invariant subspace. So what if, instead of having this relationship, we have AQ1 minus Q1S, instead of being 0, it's a matrix E1, so that this represents some sort of error. So can we get any useful information from this about, in terms of approximate eigenvalues and eigenvectors? So, all right, you all bore me down with your faces of misery, so I'm going to do a quick version, as I'm not going to actually work out for proofs, but I do want to share with you the results. So, this error expression, so the Frobenius norm of E1. So E1 is defined to be AQ1 minus Q1S. Is minimized by choosing S equal to the expression I gave for it earlier, Q1 transpose AQ1. So it's kind of like a more generalized version of a Rayleigh quotient. A Rayleigh quotient, we had just a vector transpose A times the same vector. Now we have a matrix. So it's almost like a matrix-valued Rayleigh quotient. So this is what we're probably going to time to actually prove this. And then another result is if I let S, now S is also going to be a symmetric matrix. So it has this kind of a sure decomposition. So this is a uppercase Greek letter theta. So theta is diagonal matrix, R by R matrix, and it has these diagonal entries. So those are the eigenvalues of S. And then the columns of U are the eigenvectors. So if I take U and multiply that by Q1, so this is N by R, this is R by R. So the product is going to be also N by R. So let's give its columns names. Okay. Now, so therefore it can be shown that AYK minus theta KYK is a 2 norm. Now, we'd like this to be 0, in which case YK would be an eigenvector and theta K would be the eigenvalue. But it's not, it's off to a certain degree. But we can come up with a bound for the error in terms of the other entities involved. So identity minus Q1 transpose, AQ1, 2 norm. Okay, which is the same thing as, if I were to work this out, that'd be AQ1 minus Q1S. So that's the 2 norm of this error matrix here. So if I could make this small somehow, if I could choose my Q1, choosing Q1 to get an exact invariant subspace, that's a tall order. But what if I could choose them to get an approximate variant subspace with this error, then that bounds the error in these approximate eigenvalues and eigenvectors. And so some terminology here. the pair theta k and yk is called a Ritz pair. So theta k is called a Ritz value, and yk is called a Ritz vector. So these are approximate eigenvalue eigenvector pairs. Okay. Now, let me find the right page here, but I can wrap up. Okay. Now, I can talk about one particular choice of Q1. Because right now, all I specify is that the columns of Q1 are orthonormal. They could be any set of orthonormal vectors. So suppose I choose the columns of Q1 in a pre-log subspace. So I choose some vector, I'll just go with Q1, whatever it is, then I keep multiplying by A. So if I choose my columns of Q1 based on that, then in order to get Q1, so if I choose Q1, sorry, my notation is stepping on each other's toes. If I choose the vector little q1, I could generate the matrix big Q1, capital Q1, using Lanczos, which you guys have already had some exposure to. And the result of that is A Q1 equal to Q1 T plus, okay. If I perform K iterations of Lanczos, QK plus 1, EK transpose. So this is the capital E1. In other words, we have an idea of what it looks like now. And TK is Q1 transpose A Q1. In other words, it's a matrix S from earlier. But it's a tridiagonal matrix that contains the alphas and betas that are generated by Lanczos. What that means is, if I look at the Ritz pairs, and I can give a more concrete expression for the error. It's just beta k absolute value times the absolute value of ukj, where the matrix U is from here. It's the eigenvalue eigenvector decomposition of my matrix S, or TK in this case. So, all what Lanczos does is it keeps going until this beta is below a certain tolerance. Once that gets small, we know we've obtained pretty much an exact invariant subspace, except for a round-off error. All right. So this is one approach to computing at least selected eigenvalues and eigenvectors of a symmetric matrix, is running a Lanczos algorithm. And there's theory to show that the eigenvalues, the Ritz values, the theta k's here, it's a theta, believe it or not, these Ritz values converge pretty quickly to the largest and smallest, the extremal eigenvalues of A. So we've seen Lanczos from the point of view of solving linear systems, but really, it's probably its best use is what's most effective for is computing these extremal eigenvalues. And then I've already used this for in my research involving quadrature, but all of that is related. So, so at least we have a way to approximate invariant subspace using Lanczos, so that generates this Krylov subspace. Okay, so that's sort of like a, okay, I guess I only presented it because it's kind of like a backdoor into my research program, but whatever. Okay, well, I think we've all suffered enough. So, so Wednesday, we've talked about the singular value decomposition. You've dealt with it before. How do we actually compute it? So that'll be the subject of Wednesday.